So in this lecture we're going to talk about composition, which is a hugely important topic, because composition is what allows us to build complex structures, complex things out of simple units. And the opposite of composition is extension, really. So if we think sort of a classical example of something composable is Legos. Tiny little pieces, pre-defined pieces that do one thing, and you can combine them in many ways to build fantastic structures. As like, for example, this thing. I'm a great fan of Legos. The Saturn V rocket in Lego, and it's all detachable, and you know, this is fantastic things. An example of something extensible, on the other hand, is this. It's knitted or woven, which means that there's a lot of little things that have been woven together. Now, if I want to add make my Saturn rocket into something slightly larger and put in an extra stage on it, it's easy. I can pull it apart and I can add this thing and I can put it together again, which is sort of the hallmark of composable things. It's easy. This, I have to cut the hole in it. It's hopeless. Or I have to open up the whole thing and then try to... it's quite easy to extend it though. I can just continue sort of knitting on this thing and it will become longer and longer, and then I have a nice skirt instead. But the good thing with this composable stuff is that we start with something simple which we can test, we know it works, and we can add these things together in a controlled way. Now, in computer programs, and we already talked about composition a little bit, so we're gonna repeat some of the most important aspects because this is so important. So in computer science and computer programs, how does this work? Well, one of the first things we can note is that data is composable. Like we have various types of representations of data, but that's sort of irrelevant in a way. But data composes, raw data. So, for example, we have learned about products so far, and we know that the product is basically a pair is a product. So we can just write any pair as an A times a B, right? So that's one way of combining things to form a product. But now we're going to look at another way of forming a unify things. And that's, I'm going to use a symbol plus, which is maybe a sum, maybe not. We can think of this is just a symbol. It will be just a symbol for append. We'll talk more about this and formalize this a little bit more when we talk about monoids later. But for now, this is just an append thing. Now, data. How do we compose data? Well, if I have two lists, and in F#, of course, these have to be lists of the same type. But in general, if I have two lists, how can I combine them? Well, I can combine them in two ways, really. One is to form the product, which would be a list of lists, like this, or a pair of lists, if we like. But you know, if we're going to have you say that when we compose them, we get the same data type out. So then we would get a list of lists. The other way we can do it is, of course, by using this plus operator, and that's basically just concatenate the list, append the one list to another, and now we have a longer list. The same holds true for dictionaries, maps and sets, dictionaries. If I have two dictionaries, well, I can form a pair of dictionaries. That's maybe useful, but not so interesting. But if I have two dictionaries, I can just say, okay, fine, combine these two, and now I have a larger dictionary. Data composes naturally. If I have two strings, well, I can form a pair of strings, or I can concatenate them and now I have a longer string. So, how about objects? How do objects compose? I don't know, really. It's not really defined. Like if you take two objects or two classes, how do we compose these things? Well, we can do extension. Inheritance is extension of the thing. That we know, that's well defined. But then, or you can make a pair of objects, but that wouldn't really be probably what you were looking for. So we want to do this plus thing for an object. How would we do it? Well, one thing that you need to do is that you need to go in for the class that you want to compose, or the classes, and define a plus operator for it, for the particular class that you want to compose it with. And then if some new class comes along, a new type of object that you want to compose, then you have to add that operator, and then so on and so on and so on. It's a lot of work, and you have to do the work yourself. It doesn't compose naturally. It's something that we need as programmers to define. And that makes objects they're non-composable, usually. Of course, if you're doing JavaScript, then there's no problem because it's basically just a dictionary and you just merge the dictionaries and voila, you're done. But that's a kind of special case though. You can't do that with C++. Right. So that was data. But there's another piece to this, and of course that's functions, and that's the most important piece that we are interested in. Because data is important, of course, but what we are really interested in is building functionality, complex functionality from simple pieces. And one of the examples, sort of classical examples, if we just go to the Unix shell, and we have a shell prompt, and we can say stuff like cat foo.txt pipe sort pipe unique pipe tr all small a's to capital A's, for example. So that's a useless little pipeline there, but what we see here is that we are using some tiny little programs that do one thing and one thing only. And then you feed it into a new program so that the output of the first one becomes the input of the second one, which becomes the output of that one becomes the input, and so on until we hit the end and we get up the answer. This is composition. So how do we do this in programming inside of Sharp? Well, function composition. And there are many ways to do this. And I'm going to start with the idiomatic F-sharp way of doing this. And that's basically like this. Let's create a function to compose functions. So one way to do this is that we do let, and we want this composition thing, of course, to be a inline function, and not a prefix function, and I'm going to define this pipe operator like this. And it's going to take 2 arguments and produce a result. So actually, I'm just going to write the signature for this thing. So this thing here takes an A, and it takes a function from A to B, and it produces a B. And this is a silly little function, and we can implement this. So we can say let, and it takes some x. This is the A. It takes an f, and it applies f to x, and we're done. So how does this work then? Well, it works like this. Suppose I have a function, something like, I don't know, you can just do let g equals x squared, for example, for something simple. Now I can, instead of saying g sorry, g of x, instead of saying g5, I can say 5 pipe g. And it doesn't look like we've gained very much. We just made an extra function call and made our program slower. Hooray. And we can write it in this weird way instead. That's not very useful. But this is, yeah, so all this thing is, it just flips, it makes an inline function which flips the argument. So it takes an argument and gives it to the function. So you say xf, fx. Hooray. But remember now that g here produces some kind of output, which will be a b in this case, right? So now I can have another function which takes a b and produces a c. So now I can say, oh, that might be h. And now we can pipe this into q, and so on and so on and so on. Now we can start building all these long pipelines. And now we have function composition. Now we're able to say, hooray! I can build this whole complex pipeline exactly like on the Unix shell. Very useful. Now, of course, we can flip things around. So we can define another function, which could be defined like this, which takes a function from a to b and an a and produces a b. And now you can say something like f5, which is exactly the same as saying f5. But there's an operator precedence rules and associativity and so on. So this is actually like when you have parentheses, this would be like having things parenthesized like this. It's right associative. So you can avoid parentheses. Usually this scheme here of using this operator is frowned upon, and please don't do it unless you have a very good reason to do so. And you can always find good reasons. So it exists for a reason, but you probably don't want to use the backward composition thing. All right. So that is the F-sharp pipelining. Oh my good grief. Because I talked about these things a couple of lectures ago, but then you weren't very well versed in type signatures and maybe not so super well versed in thinking about functions, and we hadn't talked about lambda calculus, and we hadn't talked about all these things. And now these things should come naturally. And the interesting thing about this pipe operator here that I showed you, I should probably write it up again. This one here. Let fx xf equals fx, with this, of course, a signature of a to b, the whole thing producing a b, right? This is pretty much how it's defined in the library. So when you're doing pipelining in F-sharp, there's no special language feature for pipelining. It's not built into the language in any way. It's just a function. It's just a function. That's important. Right. If you go to languages like Haskell, this is not the common way of doing function composition. And in fact, this is sort of not, we're not really, well, we're doing function composition, but this is sort of, we are giving it already an argument. So what if I wanted to produce a function by composing other functions? This is related to the point-free notation that I talked about, where you can sort of skip the argument, right? So in math, we have this f g of x. What this means strictly mathematically is the f of g of x. It's function composition. It's just written like this. So this means, okay, we're going to call g on x and get the result from that, and we're going to feed it into f, and then so that's function composition, right? So now we want to produce this bit here and give it a name. So I can say h of x equals f of x. Yeah. So let's look at how we can do this, because we can define a slight variation on the theme. I'm going to keep this one up. So this dot here, I'm going to do it now in the reverse order, and then we'll look at it in the other order first, because this is the order that you typically use in F sharp, and then we're going to look at the one which you typically use in Haskell. All right, so let's define a new function. Let, and this is also going to be a inline function. Let me write up the signature first. So we're going to call this forward composition, so it will work the same way as this pipelining, in the same sort of order. Right? So this is a function which takes a function from A to B, and it takes a function from B to C, and it takes an A and it produces a C. All right? So how does this work? Well, this A, so you have this function. It takes three arguments. It's like a function, it takes a function, and it takes an argument of A here. So this A will get fed to the first function, which will produce a B. That B is going to be fed into the second function, which will produce a C, which we get back as a result. It's that simple. There's no magic here. Now, the interesting thing happens that if we actually would add parentheses here, so now you would see that this is a function of two arguments, like the parentheses are really strictly not necessary, you know, partial application and la la la. But now we have a function which takes two arguments. It takes an A to a B, and takes a B to a C, and it produces a new function A to C. Which is exactly what we need for our new function. Right, so let's see how we can implement this guy. So that was I'm going to remove the signature on this guy, and now we can see, okay, how would we implement this? Right, so it takes an F, and it takes a G, and it takes an X. Right? And now, first thing we do is we apply F to X. Right. So the first thing we want to do is want to apply F to X, right? Because the A is going to go into, this is F, and this is G. So the X will go into F. F is applied to X. And that will produce a B, which should go into G, which means that, and there we go. We have implemented function composition. Now, strictly in mathematical terms, if you would write this with mathematical syntax, this would be G of F of X. First we do F, then we do G. But we can of course reverse the arrows on this thing, and we can write this the Haskell way. In Haskell, this operator is actually called dot. So that you actually would write something like G dot F, which is pretty nice. Right. We can reverse the arrows on this thing, so we can say, well, okay, so just all we do is say, well, B to C, just flip these two arguments, because the order of arguments is not really important for the function, so you can just flip them around. So if I flip these two, I will actually get this operator. You can do that as an exercise. It's easy. And then you get sort of the proper sort of how mathematicians would write it with F G of X. All right, so how do we use this thing? Well, suppose now that I have two functions. I have an f, we can say let f of x equals, well, x plus 1, and let g of x equals string. Right, so f will now add 1, and g will now and g will turn it into a string. So now we have different types here, right? So I can't feed the x into the string x, of course. So now what we do, we can create the function h, let h equals, and then we have maybe have the x in here explicitly to start with, then we can get rid of it. So x is an integer. The whole thing here is int to string. So now we can say, okay, first I need to call f, because that takes an int. It produces an int. So now I can say f, and I can compose that with g, and then we call the whole thing with x. And of course, we now can get rid of the x's. And we can do it like this. And now, so what will happen here is that this is now int to string. This was int to int, and this is int to string. So what will happen is I will feed it an int, goes into f, it produces an int, which is accepted by g, and it produces a string. And I can have the x explicitly like this, or I can get rid of it, and we can just compose things like this. So this is a very compact and nice way of doing things, but not so common in F#. So you can just as well, you could just write this in the other way, say h prime here, x would be x pipe f pipe g. Same thing. Two different ways of doing the same thing. No practical difference whatsoever. So this is function composition. So, and that's basically all I had to say about this. We're going to continue our quest for understanding compositions in various ways in the next upcoming lectures. So we will be talking about functors, and we will be talking about applicative functors, monads or computation expressions, and monoids. And all of these are essentially just aspects of composition in various ways. So until then.